Um, Hello, everyone. Um, I've been a part of this seminar series for a while. I've been chairing the America time zone, uh, and I'm really glad that this community is still going. Um, I'm leaving my position at USC in a month, and I decided to take this opportunity to present the work that our group has been doing um, to advance quantum annealing towards applications. Uh, but to do that, I'll need to explain to you what is the scaling advantage and why is our group, and our group, I mean the Daniel Lidar's group, and just a postdoc and then research sciences, the staff research scientists there, uh, why our group is focusing on this scaling advantage that much, not just for quantum annealers, also now we are doing the same analysis for gate-based computers as well. So the idea of a scaling comparison between two computational methods comes from complexity theory. However, this is a very application taste of it that really doesn't think about large n limit like a complexity theory does. Instead, it thinks for of finite n uh, and it thinks about comparing the runtime of different algorithms. So first we need to define, as it is done in complexity theory, a family of problem for every system size n. And then we need to compute something called time to solution, which is a little bit more careful way to define how long does it take for an algorithm or a method or a hardware solve a particular computational problem. Uh, and that time to solution will probably depend on a bunch of parameters that this particular solver has. So we will need to optimize all of those parameters for every system size, but not for individual problem, just we optimize parameters once for the whole family. And then we put points on this plot where there is a problem size on one axis, and then there's time to solution or its logarithm on another axis. For if a problem is complicated and it takes exponential time in the problem size to solve, then we will probably need to take a logarithm of the time to solution to have a linear fit. So the last point here is our hope that we will be able to fit a line through these points. And in particular, what we rely on here is that there isn't a drastic change in the function of time to solution as a function of n at some intermediate n between the n's that we care about. And the n's that we care about are between the sizes of quantum annealers or some sort of quantum computers that can solve problems of interest today and the size that we can realistically build in the future. So I would say between 100 variables and 10,000 variables. So I'm talking about noisy intermediate scale quantum devices. And the reason why we want to look at the scaling is that no matter what is the absolute time difference today, the scaling will overtake it. And the question, should we build a solver, a quantum computer of a particular size, really depends on what is the difference between scalings, because as we go a few orders of magnitude in sizes, uh, the scaling will multiply any kind of difference that we have. So that is the only question that this kind of scaling comparison is meant to answer. So these lines are not meant to continue all the way to infinity. They will probably turn at some point. It's just we're good as long as they turn further away than, say, 10,000 qubits. The problem, however, is that anytime people attempted this kind of scaling comparison of quantum annealers specifically as solvers of optimization problems with the state-of-the-art solvers of optimization problems, The results were opposite of what we expected. So the slope of a line drawn through the points of a quantum device was actually worse than the slope of a best classical method. And I think it's very reasonable to ask questions. Why is the slope worse, and can we actually make it better? And it turns out that yes, we can. There are two key ideas that are needed, though, that were absent from the previous works in this space. One idea is that we need to use some sort of error correction. And another idea is that instead of looking at the exact optimization, so finding the global minimum of some function, we need to look at approximate optimization, so getting epsilon close to the global minimum of that function. So that second idea is sort of my contribution because I was talking about it for years and years until people in my group actually done it. But other than that, I'm presenting the work of other people in my group in this part of my talk. So how do we do error correction, this first idea on quantum annealers? The first quantum annealer that became available had this chimera graph where the unit cell of a lattice is depicted in figure A, and people decided to use four qubits. One of them used as a penalty connected to other three. And this is kind of a ferromagnetic cluster of qubits. So all of them are either up or down. And you can think about it as penalty enforcing a repetition code on those three qubits. The repetition code corrects one error. So this is the simplest possible error correction one can think of. And it actually works pretty well, as shown in all of these papers. And there's a penalty strength that we need to specify, which will be one of those parameters that we will optimize for every problem set. The more modern quantum annealers that came out of D-Wave actually have a different graph, which is called the Pegasus graph. And there are different ways to choose this four qubits on a Pegasus graph. And in particular, the people in our group, Umberto, who was a grad student at the time, chose it in this way so that the resulting logical graph is interesting. And he chose that sometimes three of the qubits lie in one unit cell and the fourth one lies in another. And that's how he creates a graph with an interesting connectivity. So this is the graph that he created. I would call it a quantum annealing correction compatible graph or QSE compatible graph. Uh, on the specific type of D-Wave machine that we had available, we could have a slightly over 1,000 logical qubits uh, of this graph. Uh, and this graph has degree 5, roughly. Now we need to define a problem on this graph. And the simplest problem and the reasonably general problem that we can start with is a spin glass, which means that every vertex on the graph has a spin and it's coupled to the neighbors by some random value drawn from this discrete set. Um, and on a specific device, we could vary the system sizes from 5 to 15. And as I said, for every system size, we have a family of problems defined by the realizations of this randomness. Then we optimize parameters for each system size, and this is the uh, penalty strength. Another parameter is something called anneal time, which is very important, but I'm not going to go into a lot of details about it. And here are the other parameters and choices that we made for completeness. And now I'm going to explain the second idea, which is what is uh, uh, the specific definition of approximate optimization. So the idea here is that D-Wave and any quantum annealer really, by its very definition that we're trying to anneal it for a finite time, it's not going to sample the ground state, right? It's going to sample some sort of low temperature state. And the natural computational task corresponding to low temperature sampling is a time to epsilon. So we want to be within epsilon of the ground state, and specifically we want it size extensive so that we can use the same epsilon for different system sizes. So In the units where there's no shift in energies, we just multiply the difference between the state that we found and the state that is the true ground state that was found by running the best classical solver for a very long time. And this difference, uh, oh, sorry, this is just the infinite temperature state. So essentially, we multiply the scale of the Hamiltonian by epsilon, and that is the window within which we need to be. The state that we found, so minus the ground state needs to be less than or equal than this. Good. And on the right, we have formulas that just define the time to solution and time to epsilon exactly, because whatever solver we have will probably solve this problem with some probability, and we want this problem solved with 99% probability, specifically just to be concrete. And this allows us to recalculate the runtime of the solver, which is this anneal time TF, into the time to solution or time to epsilon. And long story short, after we do both of those things, we actually get scaling advantage for very specific small region in epsilon and other parameters. So for epsilon, that's about 1% relative error. A best known classical solver has a slope of 1.9. A quantum annealing without correction on D wave has slope of 2, and quantum annealing with correction has slope of 1.4. Note that this is a log-log plot, so we don't get problems where the time scales exponentially with the system size. These problems are relatively easy, even though the prefactors are pretty big, so the classical solvers will struggle at large sizes. But still, it is a actual scaling advantage of D-Wave with respect to the best classical solver. I think it is a first of its kind. And this is the end of the first half of my talk. So if there are any questions, I should probably take them now before I talk about something completely different.
Can I ask a question?
Yeah, absolutely.
I just want to just understand this figure a bit more clearly. So when you make the comparison between the classical and quantum annealers, I guess the QAC is the time to epsilon calculation.
Yes. Yes, that's
And
correct.
for the classical, are you also compromising, as it were, the exactness of finding the ground state, or?
Yes, the classical solver solves exactly the same problem. So as soon as it finds the state that is within epsilon, then we consider that it has succeeded.
I see. So, okay. So it seems that there is a significant cost associated with trying to find the exact ground state with quantum annealing, which is
Yes, so the way I think about it is that quantum annealers naturally are not ground state finders, right? So they stay in some state that has a distribution that corresponds to some temperature. It's almost impossible for them to drop all the way to the ground state in the regime where some dynamics is happening.
I see. Okay. Interesting.
Okay, so I have a question, so apologies for arriving late.
Oh, no worries.
Unanticipated delays in my cycling. Anyway, I'm looking at the small size ones. You've got a little C next to them where you haven't put the fit. So there's some asymptoting going on here, like the low end. So what's going on at the smaller sizes that they're not reliable?
Well, so this is just a general methodology that we have where we will use our fit on not all of the data points, but on the kind of the biggest data points that we have. And I think it is fairly common that at small sizes, there are some finite size effects that tend to wash away for larger sizes. So people have been plotting these plots for a long time, and I guess by this time they have an intuition that you shouldn't really use those points for scaling. However, we don't really know what is the function that governs this time to epsilon, time to solution as a function of system size. So we don't really know what's going on there. But essentially, just by looking at these plots, choosing to throw them away was a kind of human decision, right? So we decided that if we throw them away, then our predictions will be best for the points that are even larger sizes.
Have you looked at the effective temperature at the different sizes? I'm just wondering if that's the thing that is not scaling. You see
Right.
or
So
changing, yeah. And that
so
was how epsilon works in that setting, right?
I think that that's a good point. So this epsilon is corresponds to some effective temperature. However, the real device may prepare state with effective temperature that slightly kind of varies as the size changes. I think that earlier works have looked at that. I don't think this particular work has looked at it, but I think here the deviations are small, so probably they decided that it's not worth uh, digging into them because I guess the hardest part was just to get these points to lay on the line at all.
Oh, sure. It's just that, yeah, some problems I've worked with, you get the scaling from very small sizes and some you don't. So, and that's problem dependent, just how the problem.
Yes, absolutely, yes.
So,
So yeah, thank you for your questions. So I will move on now.
yes.
And we got this result for problems that are native. So this quantum annealing correction compatible graph was just a subgraph of the Pegasus graph. However, the real application problems are actually not native to any of the graphs that have been fabricated to date. They are usually fully connected. And here on the right, we have a figure from different paper, also from our group, where we had a planted solution instance that kind of is a pretty good approximation of what those fully connected problems look like. And we see that for those problems, because we have to embed a fully connected problem in using minor embedding onto the hardware graph, the solver time takes a huge hit. So now the slope is not even close to any of the slopes of the classical solvers that are working directly on the fully connected graph. And this now is exponential, so essentially the log scale versus the linear scale. So there is a change in exponent when we embed, and this is what I call an exponential slowdown. And I think the way the field is going to develop is that it will take us about 20 years to get rid of this exponential slowdown. But the most important and positive message is that it is, at least in principle, possible to get rid of this exponential slowdown. And there is an idea, both experimental and theoretical, of how to get rid of it. And it goes by the name of paramagnetic trees. Um, there is a patent even for it, and there's also early experimental demonstrations. The reason why it's called trees is because the early drawings for this idea kind of looked like there is a tree growing of each of those qubits on the outside, and the goal is to connect each of those qubits to every other one. And the reason why it's called a paramagnetic because it is in contrast to minor embedding, which was the previous way of embedding fully connected problems, because minor embedding essentially stores the state of each of those qubits in a ferromagnet. And paramagnet doesn't store the state of any of these qubits. Instead, it serves as a gapped mediator of interactions between those qubits. And here's a small footnote, is that if the mediator was gapless, then it not only introduces interactions, but also dissipation. So it needs to be gapped. And here is a theoretical result that is mine on how this gapped mediator works. So essentially, I describe how to simulate a fully connected Hamiltonian in a local architecture. And the reason why it helps to get rid of this exponential slowdown is actually relatively simple to explain. So the idea is that so this simulation is very good, and it implements the entire spectrum. The only cost we pay is a polynomial reduction in energy scale. So, and in particular, inside of that spectrum, there is a gap that determines the time scale of quantum annealing. So that gap, which is exponentially small, and that exponent determines the time scale of whatever exponent we had in those classical or quantum plots on the native graphs. So that exponentially small gap will only experience polynomial reduction using my embedding technique. And because of that, the exponent will not change. So that's the idea. And now we will forget about annealing for a bit and just talk about how to embed the all-to-all coupling in a local architecture. So as I said, we want to embed the quantum Hamiltonian. So there is a transverse field on, and there is some spectrum corresponding to the logical fully connected problem. And we want the spectrum to be faithfully represented in the low energy theory of whatever hardware we have. And we also want to be able to measure some degrees of freedom in that hardware and actually get the logical degrees of freedom. And we set our graph to have degree 2s for concreteness. And we know that working with fully connected problem is actually relatively easy for the gate-based device if we use any of the standard quantum simulation algorithms, because no matter what the hardware connectivity is, we can use swap gates to just move qubits around and have them all talk to each other. However, in analog devices, Hamiltonian is always on. So we can't just use swaps, and we need to do something different. And specifically, I am interested in what we can do in the superconducting qubits kind of setting. However, our results are also applicable to the trapped ions. So in this slide, I'm not going to go into too much detail, but essentially, I need to define mathematically what it means to have a realistic layout of elements on a two-dimensional chip. So in particular, I want to make sure that it's impossible to have an infinite density of elements. And once I set it up, I can set the goal, which is that I want to implement just a transverse field Ising model on that graph that was in the previous slide. But I want to use my two-dimensional locally connected hardware. Now, the result here is that it can be done. And the resulting effective Hamiltonian, it is described by target, it is a target Hamiltonian up to some error. And there is also a reduction factor in front, because this low energy low energy subspace of our hardware Hamiltonian, well, essentially it has a small width, right? So this width is the reduction factor alpha. And the main result is that I have proven that this reduction factor is no less than polynomial, so specifically 1 over n to the 6. So if we had an exponentially small gap in this spectrum, then it will experience a polynomial reduction, but if that gap is what determines our scaling, then the exponent of that gap will not change. So that is the purely theoretical result here. Now let's get back to the annealing and see if we try to use something like this construction and actually build an annealing schedule. What does the schedule look like? The simplest possible schedule, but not the optimal one, looks as follows. So we have two qubits, this large black circles, and we have the interaction mediator, which here is also made of qubits. So, and the mediator is connected to both of the qubits, but we say that the left connection is going to be annealed with the same coefficient as the z terms in our annealing Hamiltonian. But everything else is just kept constant. So essentially, we have three different annealing schedules. One is the transverse field annealing that goes down, the z field at the z terms in the Hamiltonian that goes up, and then there are also the interactions, ZZ interactions and transverse fields in the mediator, and also this interaction over here that are just kept constant throughout the entire process. So currently, the wave does not have that capability, as far as I know. It is possible to do that with Rydberg atoms. However, they also haven't made that capability available to the public. Maybe if we ask them nicely, they will. Um, so that is the simplest possible set of schedules that I can present that realizes this idea of paramagnetic trees. However, as I said, it's not optimal. Here I'm trying to optimize the effective coupling between two qubits. So with coefficients of the mediator going up to 1, I was able to get effective coupling 0.27 for 4-qubit coupler chain. So think about it as like the corresponding minor embedding would have a chains of length 5. So for example, this qubit and then this 4. But instead, we're using the same minor embedded graph to have mediators. And now we only had like a reduction in energy scale by a factor of 1/4 or something. And we have implemented the annealing schedule. It is a little bit different because the coefficient of transverse field goes only up to 0.5. And also we see that we didn't implement the transverse field exactly. There's some error here. But other than that, this is the schedule, the logical schedule that we have implemented. So this is the example where I tried to get the strongest possible effective coupling. And the schedules that had to make that happen look kind of complicated. So there are many different stages where there are different regimes that are happening here. And essentially, locally, this kind of constructions can be optimized by hand, and then it can be just in a modular way laid out for a bigger annealer. So that is the general idea, hopefully, that illustrates how these paramagnetic trees work. And that is also the end of my talk. Thank you, and let me know if you have any questions. So I don't hear if anybody is speaking.
Sorry, I was on mute, so that was why.
Oh,
That was my fault.
I
So
see.
so does anyone have any questions on any part of the talk? So I have a question. So the second half with the chains you were showing, the first
Yes.
thing you showed was that circle with the qubits in a circle and then the trees, right? So
Yes.
am I supposed to see what you've done with a chain as the arcs in that circle?
Yes. So, for example, like there's a qubit 8 that's connected through 4 qubits to the qubit 4. However, this was an early picture, so the final graph that I'm using doesn't look like this at all.
Okay, but yeah, so there are better ways to do it than this. I mean,
Well, I don't know if better, but essentially, I briefly mentioned it that actually this construction uses the same graph as minor embedding.
okay.
So, but instead of a chain of ferromagnetically connected qubits, you use just one qubit to store your logical state and have other qubits be mediators.
Okay, I missed that bit of the transition that you take your minor embedding, but you change what you do with the chain. Now
Yes,
I
yes.
get it. Now I get it. Thank you.
Yeah, I didn't go into too much details about that. So sorry about that.
Sure. But that makes a lot of sense. That yes, because having to have all the strong ferromagnetic links really limits what you can do with the rest of the couplings. And if you can do something better, yeah, then
Yeah,
you
the
don't
way
take the hit on the range reduction.
Yes, the way I think about it is that a ferromagnetic chain is essentially a classical variable,
Mhm.
and we want to keep it quantum.
Yes, definitely. So do we have more questions? I guess I have one more. You're saying, so you've tried this in simulation, obviously, and hardware. It's not far off what you can do with the Rydbergs currently, I think, but are you talking to them about testing actual implementations?
Well, I hope to communicate this eventually. I definitely tried before, but I'm sure they have a lot of exciting things to do. So I don't think I communicated it properly yet.
Okay.
So I'm trying.
Yeah, because no, it just happens. I was learning what QERA can currently do. And yeah, it's not very far off there's a certain amount of local control.
So I should say that the problem there is that since they don't fully control the J's,
Mhm.
essentially they have to do a lot of tricks to just have any sort of non-planarity at all in their graph.
Yeah.
And essentially to realize this kind of idea, well, first of all, I guess what I should say is that the tricks that they're using are not powerful enough, and having this idea around as another tool will let them do much more.
Yeah.
However, it also requires a lot of work just to kind of figure out for every little trick that you're using, for every little gadget that you're using, what is the best optimal way to use it.
Yes, that was my other thought, is that you can't find the optimal settings, because that's as hard as the original problem or harder. But so you have to have some sort of heuristics that are going to be good enough to gain.
Well, as I said, there is an inherent locality to this because our hardware graph is assumed to be local, and then all of these constructions are local perturbation theory constructions. So, in some sense, to optimize this kind of embedding, you only ever need to solve 10 or 20 qubit problems.
Mhm. Okay. Yes. No, again, I was thinking of the original circle where you have Y connections in it, and then you have one chain affected by another chain because they've got common links.
Yeah, it looks like we have a question.
Good. So Heda, please ask your question.
Thanks. Yeah, it's a very just quick question about the earlier part of your talk. I mean, I just wanted to get a better sense of what kind of classical solvers you were comparing against. Were these like tensor network methods or some other methods like?
Oh, right. So this is optimization, right? So I don't know how to do optimization with tensor networks. So this solver over here is something called parallel tempering isoenergetic cluster moves.
I see. Okay.
And it is a very advanced version of simulated annealing, where you have a bunch of replicas and you swap them around. You also have a non-local move that swaps half of your spins at once. So, and those things together tend to solve most problems.
Yeah, okay. Well, that makes sense. All right.
And by the way, the reason why it has like 10 to the 4 up to 10 to the 6 kind of overall wall clock runtime here is not because this is how good this method is. Like it could be much faster. It's just because so my friend was not really optimizing the performance here. He was only trying to extract the slope. That's why the overall scale here is so big. It's very likely that
So
it
could
can
be
drop
shifted,
some orders of
basically.
magnitude.
Yeah.
What do you say?
So it could be shifted, you're saying, the graph.
Yes.
Okay. Okay, thank you. Yeah.
Yes, it can be difficult to extract scalings from classical solvers because they often do portfolio things, depending on what you feed them. So you have to get a pure solver, and that's not necessarily the absolute best in order to get the scaling out sometimes.
By the way, so on the right plot, we can kind of see it because I think one of these points is the PTICM run on a normal computer, and another is this FPGA kind of Fujitsu or something, digital annealer. I don't remember. I don't remember which, but there's also a coherentizing machine here somewhere, I think. So you see that all of them pretty much just shift around the overall time, but the slope is more or less the same because they are using more or less the same principle.
And just remind me again. I mean, the reason the slope of the D wave is just so bad is because
Yes, because it's the only one that uses the embedded graph, right? If you try to use all these solvers on the embedded graph as well, they will also have this kind of slope. But they're using the logical graph, while the D wave is using the embedded graph.
It makes such a big difference.
Sorry, I can't hear you very well.
That's
But
why I just said it makes such a big difference. It's remarkable.
yes, absolutely.
Okay. Do we have any last questions?
Thank you for listening.
Yes, I'm not seeing more questions, so a big thank you for giving the talk at a very unsociable hour in your part of the world. We really appreciate it.
Right.
And I would advertise next week's talk, but I haven't got the details in front of me. But do come back next week for the next talk in the INQA series. Thank you very much, everybody.
Bye.